Good morning, students. Welcome to Computer Organization class. This is Veena A. Patil from Department of CSE BLE CET Vijaypur. In the last class, we have seen the video of some of the addressing mode like immediate mode, register mode, and absolute mode. Today, we are going to see different some more addressing modes. We have also seen some examples in indirect mode, and we have seen the example also like addition of n numbers. So today we will study about indexing mode and array. In indexing mode, the effective address of operand is generated by adding a constant value to the content of a register. Now, the register in this case is index register, where if I write x into parenthesis r of I, effective address will be equal to x plus the content of r of I. The constant x may be given either as an explicit number or as a symbolic name representing a numerical value. So x is defined as offset or displacement, where Ri is said to contain base address. To understand this, let's see diagrammatically. We have an instruction add 20 into parenthesis r1 comma r2. Okay. Now, in this example, the value that is contained in Ri is a memory location 10,000, and the value of x is given as a constant value as 20, and this x acts as an offset, and this x acts as an offset, and this is added to the content of Ri, and you will get the value of the new memory location where the operand is stored. Now, similar to this, we have another example wherein the offset is in the index register. Now, in this, the register is containing the value 20h, register R1 is containing 20h, and the constant value of x is the address of the memory location 10,000. Now this effective address will be equal to x plus content of R1, so which is nothing but 10,000h plus 20h, which is going to give you 10,020. So here it will be 10,000 plus 20 offset, which is going to give 10,020, and this is the location where the operand is present, and this operand is fetched and now it is added to R2, and the answer is stored in R2. Now coming to addressing modes, indexing and arraying. In general, the indexing mode it facilitates access to an operand whose location is defined relative to a reference point within the data structure in which the operand appears. Now this we can implement for two-dimensional array as well as three-dimensional array. If I am using it for two-dimensional array, it will be Ri comma Rj. So the effective address will be content of Ri plus content of Rj. And Rj here is called as the base register. Similarly, if it is a three-dimensional array, it will be written as x of Ri comma Rj. so that the effective address is equal to x plus content of Ri plus content of Rj. So it means that with respect to a reference point, we are going to access the data with the help of the offset. Now, the arrays we will study with an example as how it is implemented in array. Now, let's see here one example wherein list of students marks is given. Now, the list of student mark is stored in the memory in this fashion as shown in the figure. It contains student ID and 3 test marks. Um, for one student, 4 words of memory is allocated. That is one for the student ID and 3 words for storing the test marks. So each student has a 4-word memory block. The second student is also having 4 memory word block. Now if there are n students, there will be n such blocks. Now here n is nothing but the count. Count is nothing but number of students. So this is the way how data is going to be stored. And now let us see how to compute the sum of the scores of the test obtained by the students. Now see here, the first location in the memory is dedicated to store the, that is list. My pen is not working. So list is the name of the location where the student ID is stored, and after one word the next information, that is the test 1 marks is stored. So at least plus 4 test 1 marks is stored because each word address is differentiated by 4 bytes. So similarly at test plus 8 we have test 2 marks, and least plus 12 we have the next test marks. Now after 16 bytes I am going to get the new student information. So at least plus 16 I have next student ID, and with respect to this, after 4 bytes I have the test marks as test 1, test 2, test 3 respectively. So here we are using indexed addressing to access test marks from the list. Now let's see that. Now if base address, if it is Ri and the effective address is X, relative address is in X, then effective address will be nothing but base register Ri plus relative address X. So here you can see here, if Ri is containing 100 and X is containing 2, then the effective address that we are going to get would be 100 plus uh, content of x2. So if 100 is the beginning of the array, so with respect to the beginning of the array at a displacement of 2, you have the next value. So x can be positive or negative. Now let's see here one program program to find the sum of marks of all subjects of, it should be each, not reach, each student, and store it in memory location. In this program, I am going to use a register R0, which is going to contain the, or which is going to point to the memory location called least. So R0 will contain the address of an array called least. So what is an array? Array is nothing but it is a memory, or it is a contiguous memory, it is a block of contiguous memory location, and this block of continuous memory location which contains same type of data is given a single name. So whole block will be given a single name, and that I call as an array. Okay, so R0 is containing the memory address of the array called least. So whenever we write move hash least, it means address of least is stored in R0. We are also going to use two registers. One is R1, which is going to hold the sum of the test marks, and we are going to use R2, which will be used to store the sum into another memory location or another array called sum. So we have here sum, and to this sum R2 is pointing. Okay, now let's see. Now n is the count, as we already know. So the value of count, as that is the number of students, is stored in R4. So R4 is going to contain the count. Now the first instruction in the loop is add 4 R0 comma R1. Now since R0 is pointing at the beginning of the list, and we have already seen the beginning of the list contains student ID. It is not containing any test marks, but it is going to contain student ID. So test marks will be there after 4 bytes. That is, it will be there in the next word. So least plus 4 will contain test marks 1, then test marks 2, test marks 3 will be stored in consecutive memory locations. So it will be least plus 4, least plus 8, least plus 12th location, right? So when I write add 4 R0, R0 will be made, R0 content plus 4 will be added. So it will point, it will contain the address of the location where test 1 marks is stored, and that is added to the content of R1. Now I need test 2 marks. It is at location least plus 8. So here the offset is 8. So least plus 8 will give me the test marks of the next location, I mean next subject. Then if I need test marks 3, then I have to add to the content of R0 12, so that I will get the location of test 3 marks. So these will be stored in R0, R1. Now if you see here, in these 3 instructions we are not altering the content of R0, but we are using R0 as a reference value, and to this reference value we are just changing the offset or the displacement as 4, 8 and 12. Once all the three values or the test marks are added, we are going to move the content of R1, which is containing the sum of first student's test marks, to R2. So R2 is containing what? R2 is pointing to the memory location sum. So it will contain the marks of the first student will be placed at this location. And then I am going to clear the content of R1 so that we can add the second student's marks. Now, up till now R0 is still pointing at this location, but the next student information is stored at an offset of 16. So I need to change the content of R0 to point to this location, that is at least plus 16. So we add here constant 16 to R0. So now R0 will point to the second student ID. Now with respect to this, I am also going to change the content of R2. R2 also I am going to make it to point to the next word so that we can store the next student marks. So this also we are incrementing by 4. And since we have already performed addition for one student, so we are decrementing the count by 1. Then we are going to check, is the count greater than 0? That is the content of R0 greater than 0? If it is yes, then go to the label called loop. So it will come here at label loop. Again I am repeating the statements. Add the content of R0 with a displacement of 4 to R1. So with respect to R0, R0 is pointing here. With respect to this location, at a displacement of 4, the second student test 1 marks is there, and with respect to R0 at a displacement of 8, the test 2 marks is there, and at a displacement of 12, test 3 marks is there. So we are going to perform the same set of operation here again. Then we are going to store the value of the second student at location pointed by R2. So marks 2, let it be the marks of student 2. Then I am clearing. Then again if I want to point to the next student, I have to change the value of R0 by 16 so that the next student marks can be added. So this goes on repeating as long as the value that is there in the counter, that is R4, is greater than 0. Okay. So that is how we are supposed to deal with arrays. Now let's see. Now indexed effective address will be for indexed, it will be register content RI plus relative address Rj. Say here Rj is 100 and Ri is 2. Earlier we had seen with respect to X. Here I am taking as a content of 2 registers if it is a 2-dimensional array, so that we are going to get the effective address as Ri plus Rj. So Ri can be positive or negative. Now it will be useful when we are performing auto increment or auto decrement. Now that we can see here in relative addressing mode. In relative addressing mode, the effective address is determined by the indexed mode using the program counter in place of general purpose register. Now there we had used general purpose register, but instead of general purpose register, we are going to use here the content of program counter. Now X is a signed number. This X constant is a signed number. Now such statement where we are using whenever we are performing branch greater than 0 statement, which we have seen in the previous example. Now in such statement, this type of relative addressing mode is used. Now this location is computed by specifying it as an offset from the current value of PC. So whenever I am performing branch greater than 0, it is going to perform or compute PC in plus X. Now the branch target, that is loop, will be decided on the value of X. Now since PC will be pointing always to the next instructions, we have straight line sequencing, it will be pointing to the next instruction. But if I want to bring back the execution back to some label, then it will be decided on the basis of value of X. So the branch target may be either before or after the branch instruction, and the offset is given as a signed number. Say for example, here in the previous example, branch greater than 0 is there. Now PC will be usually pointing to the next instruction sequentially. Now if I want to make the execution to go back and start at a label called loop, then with respect to the content of PC, we are supposed to manipulate the value by giving the value of X. So usually whenever such branch statement is there, if I want to branch it to back instructions, it will be negative. If I want to branch it to forward instruction, it will be positive. Now when it is negative, the PC content, when it is added with negative value, it will get reduced so that it will point to the previous instructions. If it has to branch to ahead instructions, then X value will be positive. Okay, so you can see here in relative addressing, effective address is nothing but it is equal to PC plus relative address, that is X. Now say here if PC is 2 and X is 100, that is somewhere ahead, then when I add these two, I am going to jump to an instruction ahead. Okay, so as I told you, it could be positive or negative. So we shall see auto increment and auto decrement. In auto increment mode, the effective address of the operand is the content of a register specified in the instruction. and after accessing the operand, the content of this register are automatically incremented to point to the next item in a list. Say for example, in auto increment, we have here example Ri into parenthesis plus. It means the increment is 1 for byte sized operand and 2 for 16-bit operand and 4 for 32-bit operand. So you people have already studied I++ in your C programming. So auto increment is nothing but I is equal to I plus 1, and this one value, it depends on the instruction, that is, if it is a byte sized operand, then it will be 1. If it is 16-bit operand, it will be 2, and if it is a 32-bit operand, then the increment will be by 4. Same way, auto decrement I can write as minus R of I. Now the same previous program is rewritten here, wherein I am going to use auto increment method of addressing. So here you can see I am assigning count, I am assigning a pointer to a array called num1. I am using R0 to add the contents of the number. This is adding of n numbers, which we have already done in previous videos. We have dealt with this, the addition of n numbers. So if you see here, in the previous program, what we had done, after addition of the number, we incremented the pointer. Now here, if I am going to write add R2 plus R0, the content of R2, that is the address, is automatically incremented, and here we are taking the content of R2 as address, that is, it is containing 32-bit operand, so the content of R2 will be incremented by 4, and we are decrementing R1 and we are checking whether R1 is equal to 0. If not, I am repeating the loop, otherwise I am coming out of the loop and the sum is R0 content is stored into a memory location called sum. I hope you understood this program. We have already dealt with this. This is nothing but I have a memory called num, and the address of this is stored in R2, and the number of elements in this are n numbers are stored, right? So we are supposed to find the sum of n numbers, and to perform this, we have already seen in the previous video, but still I am trying to show it. Now to add this, I am going to take a variable called R0. So initially, the content of the memory location pointed by R2 variable is added to R0. Now after performing addition of the first number, it should point to the second number. So we are doing auto increment. So in this auto increment, it will be incremented by 4 so that it will point to the next number. Now this process goes on as long as the content of R1 is greater than 0, till we reach or we add all the n numbers this will be repeated. Okay. So in the next video we shall see assembly language.